Astronomers have identified another mysterious interstellar object speeding through our solar system. And this one is astonishingly massive, officially named 3I Atlas. It is racing along at more than 150,000 mph and could measure up to 12 meters in diameter, making it much larger than its famous predecessor. Oumuamua. Telescopes worldwide are eagerly observing its unusual glow, trajectory, and faint, misty halo, while some researchers assume it is a frozen fragment of rock or ice. Others speculate whether it could be something far stranger. Could this colossal traveler from beyond our stellar neighborhood hold answers that challenge our deepest cosmic assumptions? This extraordinary discovery unfolded in the final days of June 2025, when astronomers noticed this enigmatic visitor moving across the sky at incredible speed. Unlike ordinary comets or asteroids, 3I Atlas was quickly identified as an interstellar wanderer, the third of its kind ever confirmed. Its detection has captivated scientists, who immediately recognized its rarity. For centuries, astronomers have charted countless asteroids and comets orbiting our sun. But interstellar objects are virtually unheard of. Before the breakthrough of 2017, not a single one had been verified. With the arrival of 3I Atlas, humanity has now documented 3 within less than a decade, an astronomical rarity by any measure. This is not just cosmic debris passing by. It is a messenger from another star system, a tangible clue about distant worlds that may remain forever beyond our reach. The ongoing investigation into what it is and where it's headed has unfolded like a gripping cosmic mystery, keeping researchers awake into the night as they track its rapid journey through the solar system at a staggering 152,000 mph. To scientists, 3I Atlas is more than a discovery, it is a fleeting opportunity, a gift from the galaxy itself, carrying materials from regions we may otherwise never experience. Hashtag the discovery story. The chain of events began between June 25th and June 29th, 2025, when the Atlas system, a network known as the Asteroid Terrestrial Impact Last Alert System, was carrying out its usual scans. Based in Hawaii and South Africa, its mission is to constantly search the skies for asteroids that might pose an impact threat to Earth. On those routine nights, the system flagged a faint point of light drifting across the background stars. At first glance, it appeared to be an ordinary near-Earth object, marked down as 11PL3Z in the growing catalog. Nothing about it seemed especially unusual until more detailed scrutiny suggested otherwise. On July 1st, astronomers in Chile noticed something remarkable. The object wasn't behaving like a typical asteroid. Its orbit didn't align with paths tied to our sun, and its speed was far too high for a local solar system body. Follow-up observations on July 1st and 2nd confirmed the anomaly. This was not a native resident of our planetary system, but a transient visitor from far beyond. The investigation took a leap forward thanks to amateur astronomer Sam Dean, who revisited archived Atlas images from late June. His findings revealed earlier sightings of the same object, crucially refining its orbit and velocity calculations. By July 2nd, the Minor Planet Center had received over 100 official observations gathered from telescopes worldwide. Some images even suggested faint emissions of gas and dust, the signature of a comet. With this influx of evidence, astronomers officially named the object 3I Atlas. The 3I indicates it is the third interstellar object ever detected, while Atlas honors the system that first recorded its appearance. Paul Chodas, director of NASA's Center for Near-Earth Object Studies at JPL, emphasized just how extraordinary this discovery is. At its current velocity, he explained, there's no possibility that 3I Atlas originated within our solar system. Tracing its path backward points toward the galactic center, suggesting it emerged from another star system entirely, though which one still remains a mystery. The confirmation of a third interstellar object within such a short span of time has scientists questioning whether these mysterious visitors might be far more common than once believed. It is possible that they have always drifted silently through our solar system, unnoticed until recent advances in technology finally made detection possible. The current discovery, 3I Atlas, stands apart from countless local objects for several striking reasons. Its velocity is extraordinary, about 152,000 miles per hour. At that speed, a trip from Earth to the Moon would take less than 2 hours. Most bodies in our solar system move at a slower pace, held firmly by the pull of the Sun's gravity. This object, on the other hand, is not bound in the same way. Its sheer speed reveals its alien origin. Unlike comets or asteroids circling the Sun, its backward traced path does not close into an orbit. Instead, its trajectory leads outward toward deep space, hinting at a birthplace near the galactic center, though the exact star system remains unknown. Its brightness is another surprising feature. Harvard astronomer Avi Loeb noted that 3I is reflecting a remarkable amount of light. This suggests two possibilities: either its surface is unusually shiny or its size is immense. If its surface is dark like most space rocks, the object would need to be around 20 kilometers across to reflect this much light. Such dimensions vastly overshadow both of our earlier interstellar visitors. Oumuamua was thought to be about 100 meters long, while Comet Borisov measured roughly 400 meters. By comparison, 3I Atlas would be dozens of times larger. Adding to its intrigue is the possibility of comet-like activity. Some telescopes have captured what seems to be a faint halo of dust and gas surrounding it, a feature known as a coma. This could classify it as a comet, albeit very different from those native to our solar system. As sunlight warms the object, a more distinct tail may develop, which would offer important clues about its makeup. Its orbital path also adds to the evidence of its foreign origin. While local objects generally follow the flatter plane of our solar system, 3I Atlas arrives on a steep, plunging angle across this plane, highlighting that it did not develop alongside our planets. Each fresh observation deepens astronomers' sense that this object is not merely a rock drifting in from outside, is more like a capsule of ancient history, carrying fragments of information about a planetary system far beyond our reach. With each passing night, pointed telescopes capture details that may reshape how we view the wider universe. To grasp why this discovery holds such significance, it helps to recall the brief but remarkable history of past interstellar detections. Before 2017, humanity had never confirmed a single object from beyond the solar system. Everything observed had originated within our own neighborhood. Then, on October 19, 2017, astronomers in Hawaii spotted something strange with the Pan-STARRS telescope. The object, later named Oumuamua, meaning scout or messenger in Hawaiian, was like nothing seen before. Its shape appeared bizarre, possibly long and cigar-like, or perhaps flat and pancake-shaped, rotating in such a way that sunlight reflected off it unevenly, producing wild brightness shifts. Even stranger was its behavior as it moved away from the solar system. Rather than slowing, it gained a slight boost in speed. Inconsistent with gravity's pull alone, many attributed the effect to outgassing, where invisible jets of gas push an object like a rocket. However, others, including Loeb, suggested the daring possibility that it might be artificial, perhaps an alien light sail. Oumuamua disappeared quickly, denying scientists the chance for closer investigation and leaving behind far more questions than answers. The next chapter came in August 2019, when amateur astronomer Gennady Borisov discovered another interstellar body. Unlike Oumuamua, this second object was clearly a comet, complete with a visible tail, named 2I/Borisov in recognition of its discoverer. It was far easier to analyze since it was spotted months before closest approach. Measuring about 400 meters across, it was composed of familiar icy material, much like comets that orbit our sun. This suggested that the processes behind comet formation may be universal across star systems. While Oumuamua challenged every expectation, Borisov felt oddly familiar. Their stark differences left scientists both fascinated and puzzled. Now, with the arrival of 3I Atlas, a third point of data emerges, one that may help us determine whether Oumuamua was an oddity, whether Borisov was the norm, or whether both are part of a much larger spectrum of interstellar wanderers. The appearance of 3 such objects in under a decade, after centuries of detecting none, has made researchers consider a startling possibility that these visitors are far more common than once thought, and that technological leaps in recent years have simply opened our eyes to what was always there. Tracking the passage of 3I Atlas through our solar system is like witnessing a grand interstellar voyage in real time. An extraordinary journey that carries the mysteries of another world straight into our cosmic front yard. As of early July 2025, the newly discovered interstellar traveler is hurtling through space at more than 152,000 miles per hour. At present, it sits about 3.8 times farther from the Sun than Earth, placing it beyond Mars' orbit but still within the asteroid belt. Unlike native solar system bodies, it is not in orbit around the Sun. Instead, its path is hyperbolic, a one-way pass that will carry it through our system before sending it back into the depths of interstellar space. If astronomers attempt to trace its journey backward, its trajectory points in the direction of the Milky Way's core. Yet, locating its precise origin star is virtually impossible, since the galaxy has shifted considerably over millions of years. Like trying to identify which rain cloud created a single drop that has long since fallen. Looking forward, several notable encounters lie ahead. On October 3rd, 2025, it will swing past Mars, marking its first close pass with a planet and offering an ideal opportunity to see whether the planet's gravity makes measurable changes to its course. Then, on October 23rd, 2025, it will reach perihelion, its closest approach to the Sun. Even then, it will remain about twice as distant as Earth is from the Sun, sparing it from the extreme heating that can fragment fragile comets. This wide berth also guarantees that Earth faces no threat. In fact, our planet will be on the opposite side of the Sun during the encounter. By December 2025, it will appear closest to Earth, though still at a vast and harmless distance. Afterward, it will accelerate outward, slowly breaking free from the Sun's influence and resuming its long interstellar odyssey. This object is like a cosmic tourist on a temporary visit before resuming its endless voyage. Forged around another star system billions of years ago, it may have drifted across interstellar space for millions of years before arriving here by chance. Soon enough, it will exit as quietly as it entered, continuing on toward unknown destinations, carrying the silent record of its meeting with our Sun and planets, a record that may never be discovered unless intelligent life in another system one day encounters it. For the scientific community, this is far more than a curiosity. It is a treasure trove of information. Until recently, every asteroid, every comet studied originated within our solar system. The arrival of this object brings direct material evidence from entirely different conditions of planetary formation. It is like holding a piece of another system in our hands without having to travel across the stars. Its larger size compared to earlier interstellar visitors makes this opportunity even more valuable, as it allows researchers to gather clearer observations, richer spectra, and more detailed measurements than were possible with Oumuamua or Borisov. If the object's faint haze truly signals comet-like behavior, scientists will be able to compare its gases, ices, and dust with those of local comets. The answers could illuminate whether the chemical building blocks for life as we know it exist in abundance across the galaxy or are unique to our home system. Timing has worked in science's favor as well. Unlike Oumuamua, which was already departing when identified, this object was detected months before its closest approach. This long lead time grants astronomers the chance to deploy a wide range of telescopes and instruments for observation. The technological landscape is also dramatically improved since the first interstellar detection in 2017. The James Webb Space Telescope and other state-of-the-art observatories are now available, offering unprecedented capabilities for detailed study. Perhaps even more significant is what repeated discoveries suggest. Before 2017, such objects were predicted to appear just once every few decades. Now, 3 have been confirmed in under 10 years, reshaping those predictions. Many scientists now believe interstellar objects pass through our system much more often, possibly several times a year. Most simply escape notice because they are too faint, too small, or pass too far from Earth to detect. If the frequency of these objects is indeed higher than once thought, it provides key insights into how planetary systems evolve. It means that material is constantly being ejected from forming or aging systems, drifting across the galaxy, sometimes arriving in other systems as silent messengers of their origin. Still, questions persist. Despite its bright visibility and detailed observations, the exact classification of this object is uncertain. Is it a comet, shedding faint traces of gas and dust, or a rocky asteroid, or perhaps a type of body we have not yet defined? While its fuzzy appearance hints at cometary activity, it lacks the dramatic, long tail often associated with comets. What it truly is remains one of the greatest mysteries surrounding its passage. And decoding that mystery will be one of the main goals of the months ahead. Some researchers have proposed that the object could be what is known as a pristine comet, one that has never swung close to a star and still preserves its original store of ice. Another layer of mystery lies in its striking brightness. According to Harvard astronomer Avi Loeb, 3I Atlas is reflecting far more light than would normally be expected. If its surface is dark and rocky, like a typical asteroid, then it would need to be immense, possibly 20 kilometers across, in order to shine this brightly. On the other hand, if its surface happens to be highly reflective, the object could be significantly smaller. Pinning down its exact size and reflectivity has proven extremely difficult even with the most advanced observatories. Its rotation poses another puzzle. Normally, objects in space rotate steadily, but data gathered so far indicates that 3I Atlas may not be spinning smoothly on a consistent axis. Instead, it might be tumbling irregularly, as if thrown off balance by some major event in its history. This sort of chaotic motion could be the result of a past collision or a close gravitational encounter with another massive body that left it unstable. Questions about its origins remain unresolved. Was it formed in the relatively recent past around a nearby star? Or has it been drifting anonymously through the galaxy for billions of years? The answer could be buried in its surface characteristics and elemental composition. But current observational tools have not yet provided that level of detail. Perhaps the greatest scientific lore lies in what 3I Atlas might reveal about its home system. Every planetary system imprints a unique chemical pattern on the bodies it produces, distinct proportions of elements, rare isotopes, and particular minerals. If astronomers can decipher these fingerprints, they could indirectly study a system that will never be visited in person. Researchers are also paying attention to whether the object shows any kind of non-gravitational acceleration as it moves through the solar system. Oumuamua displayed such behavior as it exited our system in 2017, sparking heated debates about its cause. If 3I Atlas also demonstrates a similar, unexplained push, it might mean that such effects are a common trait of interstellar travelers. These mysteries make 3I Atlas much more than just another entry in the astronomy catalog. Each careful measurement carries the possibility of unlocking new clues about its past and its nature, with months still ahead to observe it before it vanishes back into interstellar space. Astronomers are racing against time to gather as much knowledge as possible. Of course, whenever something arrives from beyond the solar system, it naturally raises the most thrilling and speculative question of all. Could it be artificial? Could this object actually be constructed by intelligent life from another star? Though this idea often belongs to the realm of science fiction, it has been taken seriously in scientific circles, especially after Oumuamua's unexpected behavior. Avi Loeb famously suggested back in 2017 that Oumuamua might have been an alien sail or probe, its odd acceleration and peculiar shape hinting at possible artificial origins. Now, with 3I Atlas, he has again urged that the James Webb Space Telescope be used to check for subtle evidence of movement not explainable by gravity alone. If any such acceleration is found, it could point to some form of engineered propulsion. Still, it is important to keep expectations grounded. Non-gravitational acceleration in comets is a known natural effect, caused when solar heating turns surface ice directly into gas. The escaping vapor acts like a tiny thruster, giving the object a small boost not accounted for in purely gravitational models. This phenomenon could easily explain unexpected changes in course, what would truly set off alarm bells. However, would be behaviors or signals impossible to dismiss as natural. If the object were to suddenly change direction contrary to physics, emit radio frequencies, or display materials and isotopes that cannot arise through natural processes, then the possibility of artificial origin would have to be taken much more seriously. These would all serve as warning signs that something unusual might be happening. Another aspect astronomers are closely watching is whether 3I Atlas maintains a steady brightness or displays patterns in the way it reflects light. Natural bodies are usually irregular in shape, which causes their brightness to vary as they spin. A more consistent brightness could hint at a smoother, possibly artificial form. While it is scientifically responsible to consider the possibility of artificial origins, history shows that natural explanations are far more common. When pulsars were first detected in the 1960s, their precise radio signals led some scientists to wonder if they were alien beacons. Eventually, they were identified as fast-rotating neutron stars, strange but entirely natural. Even so, the mere possibility, however remote, that we might be studying technology from another civilization is part of what makes these discoveries so captivating. They compel us to confront the ultimate question of whether humanity is truly alone in the universe, regardless of whether 3I Atlas turns out to be a natural comet or asteroid. The very process of testing even radical ideas deepens our understanding. As Carl Sagan famously said, "Extraordinary claims demand extraordinary evidence." Although most astronomers consider it extremely unlikely that 3I Atlas is of artificial origin, they remain alert to any extraordinary evidence as it continues its journey. Observing such an object is no small challenge. Imagine trying to study a dark object that could be smaller than a city yet is racing at 152,000 mph and located billions of miles away. Doing so requires advanced technology, and fortunately, more of it is available today than at any point in human history. Astronomers from across the globe are pooling their resources, using telescopes in locations like Hawaii, Chile, and South Africa to track its position, record shifts in brightness, and study the faint light it reflects for clues about its makeup. Still, the most powerful insights come from observatories beyond Earth's atmosphere. The James Webb Space Telescope, with its massive mirror and superb infrared capabilities, is an ideal instrument for probing such an object. It can detect heat and reveal the presence of specific molecules and minerals. Astronomers have already secured Webb observation time to analyze this cosmic visitor in depth. The Hubble Space Telescope, though older, continues to play a crucial role with its ultraviolet capabilities that complement Webb's strengths. Together, they allow scientists to examine the object across multiple wavelengths. Besides visual study, astronomers are also listening. Facilities like the Very Large Array in New Mexico and the Allen Telescope Array in California are searching for unusual radio signals. An alien broadcast is not expected, but monitoring can still reveal whether the object emits radio waves as it interacts with the solar wind, a constant flow of particles streaming from the sun. As it approaches the inner system, its brightness will increase, and if it is indeed cometary, it could develop a clearer tail. That tail would provide invaluable material for analysis, since it carries gas and dust released directly from the body itself. The detection of 3I Atlas is now seen as the beginning of a transformative era in astronomy. Up until 2017, no confirmed interstellar visitor had ever been seen. Now, in less than 10 years, 3 have been identified. This is not mere coincidence, but the result of tremendous technological progress. Automated sky surveys, highly sensitive telescopes, and advanced software capable of flagging unusual movements have revolutionized the search. The likelihood is not that interstellar objects were rare in the past, but that humanity lacked the means to notice them. Soon, this capability will expand further with the Vera Rubin Observatory, which will capture wide-field images of the sky every few nights. Its enormous digital camera will create a dynamic record of celestial changes, potentially uncovering several interstellar objects each year. The data will allow scientists to answer questions that were once pure speculation. Are most of these wanderers comets or asteroids? Do they originate from interstellar systems or the outer reaches? How frequently are star systems ejecting material into interstellar space? Plans are also in development for spacecraft designed to intercept such visitors. Although 3I Atlas was found too late for a mission launch, agencies and private companies are considering rapid response probes that could be sent after the next detection if identified early enough. Beyond the scientific returns, there is a philosophical impact as well. Each interstellar object is a direct physical link to another star system, proof that material is exchanged across the galaxy. They remind us that our solar system is not an isolated bubble, but part of a larger galactic network, where fragments of one system may eventually travel through another. In this way, discoveries like 3I Atlas not only reshape astronomy, but also how we view humanity's place in the cosmos. And as this interstellar traveler continues on its path, it captures the imagination of all who look up and wonder about what secrets it might hold. Astronomers have recently detected what seems to be a secondary object moving in tandem with 3I Atlas, suggesting the interstellar traveler may have broken apart near Mars. Data from the Minor Planet Center in July 2025 indicated a fragment emerging just 1.4 astronomical units from a red planet, an occurrence so rare it has only been documented before with comets such as Shoemaker-Levy 9, which fragmented before colliding with Jupiter. NASA scientists are now assessing whether this split could alter Atlas's course or threaten missions bound for Mars. The question remains, what triggered this spontaneous breakup? And is the second object merely a natural fragment or something entirely new? Late on the night of July 25th, flag data points began to appear on the Minor Planet Center's monitoring system, the Zwicky Transient Facility, performing automated sky scans from Palomar Observatory, passed over 3I Atlas's coordinates and detected an unusual faint smudge a few arc-seconds off the expected path. Within minutes, MPC analysts were cross-verifying astrometric readings, comparing timestamps, and debating whether the anomaly was a data error or the first genuine evidence of fragmentation. Internal communication channels lit up with alerts, possible fragment, confirm ASAP, and rerunning pipeline needs second verification. Confirmation wasn't isolated to one observatory. By sunrise, both Chile's Very Large Telescope and NASA's Scout Tracking System had noticed the same anomaly. The new object wasn't an imaging glitch, it followed nearly the same hyperbolic trajectory as Atlas, trailing by less than 1/10 of a degree. Between July 28th and July 30th, MPC's central database filled with urgent entries as teams worldwide raced to determine the coordinates. The offset, though minute, remained constant across consecutive images. With 3I Atlas position 1.4 astronomical units from Mars and the opportunity for high-resolution imaging narrowing, observatories worldwide pivoted rapidly. Telescope directors debated rescheduling their existing targets to capture a potentially historic interstellar event. Hesitation gave way to urgency. Missing this observation could mean losing an unprecedented scientific opportunity. Within 72 hours, both terrestrial and orbital instruments were focused on that single region of space, eager to document the phenomenon before the fragment moved out of range. For those involved, the MPC analysts, ZTF operators, and Mars Reconnaissance Orbiter teams, the discovery represented far more than a shift change. Internal logs described sleepless efforts, last-minute reconfigurations, and a strong sense of duty to record what was unfolding. Combined data revealed a second object tracing nearly the same trajectory as Atlas, its faint signature proving it was real. The teams recognized they were observing an exceptionally rare event. Not since Shoemaker-Levy 9 had a cometary breakup been captured so clearly. Yet this time, the disintegration involved an interstellar visitor near Mars. While comet fragmentation is a known phenomenon, the conditions near Mars make this event highly unusual. Breakups typically occur close to the Sun, driven by intense solar radiation, tidal strain, or internal gas buildup that causes a nucleus to rupture. But 3I Atlas's position, 1.4 astronomical units from Mars, means it lies far from such harsh thermal environments. Moreover, as an interstellar object, only the third of its kind ever observed, its behavior defies precedence. Shoemaker-Levy 9's breakup in 1992 resulted from Jupiter's immense gravity, pulling the comet into 21 fragments before they collided spectacularly with the planet's atmosphere. Atlas's case is different. It is traveling on a hyperbolic orbit at roughly 60 kilometers per second, with Mars's relatively weak gravity offering little explanation for the split. The unexpected fragmentation has drawn the attention of mission planners tracking Martian orbiters. Even a small fragment traveling at such extreme velocities could endanger spacecraft or, if its trajectory shifts, brush against Mars's thin atmosphere, with Mars roughly 1.4 astronomical units away from Atlas's current position. The margin for safety is slim, prompting constant scrutiny of every new observation for any sign of additional fragmentation or course variation. For scientists and engineers, this event is both a landmark opportunity and a logistical challenge. A breakup of an interstellar body so close to a planetary orbit provides a rare glimpse into alien materials and structural processes previously unobserved. As Mars missions now factor in potential debris threats, the parallels with Shoemaker-Levy 9 serve as a striking reminder of cosmic vulnerability, only this time. The lesson comes from beyond our solar system, playing out near the Martian frontier. Incoming data from the Global Telescope Network soon confirmed the findings. Between July 29th and August 1st, astrometric readings precisely documented the positions of Atlas's main nucleus and the suspected fragment. Analysts mapped both against the predicted hyperbolic motion, searching for signs of non-gravitational forces such as outgassing. Over 100 recorded observations showed the two maintaining nearly identical courses, though the fragment lagged ever so slightly in speed, a detail that invited deeper investigation. Spectroscopic teams at Gemini South and the Southern African Large Telescope turned their focus to Atlas's coma, scanning for gas emissions and dust profiles. Spectra obtained around July 5th displayed a wide absorption near 2 microns, hinting at water ice, yet lacking the strong carbon dioxide and carbon monoxide markers previously associated with Atlas. The inconsistency stood out, suggesting a shift in composition or activity. Production rates appeared elevated but steady, with no abrupt spikes that would normally accompany fragmentation outbursts. Instead, the data revealed a dust-dominated coma with a relatively low gas-to-dust ratio, resembling those found in Jupiter family comets rather than the volatile-rich interstellar objects previously observed. The rotation state became another major focus of investigation. Over 72-hour observation period, light curve data from the Nordic Optical Telescope tracked subtle fluctuations in the coma's brightness and color, but revealed no signs of rapid spin-up or erratic tumbling. The nucleus appeared diffuse yet stable, showing no hints of fast rotation or chaotic motion. This steadiness puzzled some dynamicists who anticipated that a breakup would leave visible evidence of angular momentum transfer or irregular brightness variations. Instead, the photometric data displayed only a gradual brightening and a slight expansion of the coma's diameter, both consistent with normal cometary changes resulting from increased solar heating. Trajectory residuals reported by the Minor Planet Center stayed closely aligned with the predicted path, showing no abrupt jumps or unexplained distortions. If fragmentation had taken place, it left behind no clear astrometric proof, at least not in the data published so far. The anomaly, then, was not one of dramatic deviation but one of nuance, a faint and persistent companion, stable dust and gas activity, and a trajectory almost perfectly adhering to expectations. For scientists, this combination was both reassuring and perplexing. The signals were genuine, but they fit none of the typical fragmentation blueprints. The next step required tackling a range of theories, each offering a different interpretation of what the instruments had captured. By August, debate intensified and spilled beyond observatory records into international conference discussions. The annual Planetary Science meeting in Vienna, scheduled just after the discovery of the second object, became a focal point for competing ideas. Avi Loeb and his Harvard team arrived with new preprint analyses proposing that the slight velocity delay between Atlas and its companion could suggest non-gravitational acceleration, something beyond the familiar effects of outgassing. Their presentation invoked the unresolved puzzle of Oumuamua's unusual motion and proposed that propulsion-like surges, possibly due to deeply buried venting, could be responsible. Loeb's team urged the community to pursue more advanced modeling and warned against dismissing the effect as mere observational noise. In contrast, a group of veteran comet dynamicists countered strongly, drawing from decades of experience tracking solar system fragments. They emphasized that Atlas's coma, though dusty and expanding, showed no signs of the violent jets or fast rotational changes characteristic of major disintegrations. They cited the stable light curves, the absence of sharp photometric dips, and the lack of chaotic motion as evidence that no catastrophic activity had occurred. To them, the secondary object might instead be a slowly ejected cluster, caused by uneven outgassing or gentle thermal stresses separating a loosely bound piece of material. They deemed claims of exotic acceleration premature, pointing to the astrometric data's tight adherence to predicted paths. Chemical analysis further fueled the disagreements. Spectroscopic readings revealed an unusually high carbon dioxide concentration contrasted with weak water signatures, an anomaly that some deemed curious but still within accepted variations. One theory suggested that Atlas, after spending countless years in interstellar cold, might contain layers of volatile ices that react unpredictably when they warm in sunlight. Others argued that calibration inconsistencies in the July data could have distorted these spectral readings. During a closed-door session, a senior researcher urged caution, warning that publicity was racing ahead of rigorous peer analysis, and urged patience until results from the James Webb Space Telescope and Mars-based instruments were fully vetted. Meanwhile, informal conversations among attendees repeatedly returned to the same conclusion. No one was entirely sure whether Atlas had truly fragmented or was simply behaving in ways atypical for known comets. By the close of the conference, scientific opinion had clearly split into differing factions, each convinced but none fully able to explain a phenomenon that continued to resist simple categorization. Some experts urged immediate telescope observations to monitor any evolving changes, while others advocated for a slower, more methodical strategy. This debate opened the door for a detailed comparison of the competing theories as new data from Mars missions and deep space observatories continued to arrive. Interstellar visitors have entered our solar system only a few times, at least from what existing telescopic records show. When Oumuamua was first spotted in 2017, it sped through the inner solar system without forming a visible coma or tail, and without showing any signs of fragmentation. Its light curve suggested a highly elongated shape, yet observations from major facilities including Hubble, Spitzer, and Pan-STARRS all indicated a single intact trajectory. The central mystery revolved around its acceleration, which did not align with conventional cometary outgassing models. Some teams, such as those at Harvard, proposed that concealed ices or hydrogen jets could explain the anomalous boost in velocity. Others pointed to observational uncertainty, claiming faint gas emissions might have simply escaped detection. Ultimately, Oumuamua remained whole as it exited the solar system, leaving its true nature unresolved and still a matter of scientific debate. The next confirmed interstellar traveler, 2I/Borisov, appeared in 2019 and exhibited behavior far more consistent with typical comets. As it approached the Sun, Borisov developed a luminous coma and a long, dust-laden tail. Over several months of observation, astronomers tracked its progression with Hubble, the Very Large Telescope, and many ground-based instruments. Spectroscopic analysis revealed high concentrations of carbon monoxide and even traces of nickel, features uncommon among solar system comets. Despite these chemical anomalies, Borisov's nucleus stayed intact from entry to departure. No secondary body emerged, no visible fragmentation occurred, and its hyperbolic motion remained steady. The comet eventually faded after perihelion, leaving behind a dust trail and a consistent series of light curve measurements. Together, these two interstellar examples established expectations for objects entering from beyond the solar system. Both showed peculiarities: Oumuamua's unexplained acceleration and Borisov's unusual chemical composition, but neither produced fragments or companion objects. Among astronomers, the prevailing understanding is that fragmentation is exceedingly uncommon and generally results from extreme forces, such as tidal stress induced by large planets or intense solar heating near the Sun. For most comets, even those that originate beyond our system. Traveling through the inner regions rarely leads to disintegration. Their chemistry may present surprises, yet their structural integrity tends to survive the journey. This historical context shapes current deliberations surrounding Atlas's behavior. While oddities naturally generate widespread attention, experience reminds researchers that most interstellar objects pass relatively quietly, keeping their mysteries intact. NASA's Planetary Defense Coordination Office and the European Space Agency's monitoring divisions are observing 3I/Atlas with heightened concern that extends beyond pure scientific curiosity. The possible appearance of a fragment near Mars forces mission planners to assess the implications, however minor, of potential debris moving at interstellar speeds. Internal NASA documents circulated in August detail the scale of the challenge ahead, balancing research priorities, safety precautions, and mission integrity as the global effort to track 3I/Atlas intensifies. If a fragment from the split were to alter its course by even a fraction of a degree, it could potentially intersect the path of an orbiting probe or, in a less likely but still concerning case, skim Mars's upper atmosphere. The threat is not purely hypothetical. Mars is currently host to an expanding network of orbiters and landers, each relying on precisely calculated trajectory predictions to avoid collisions. The updated 2025 Planetary Defense Guidelines, scheduled for implementation later this year, now emphasize rapid response simulations to handle unexpected celestial objects. These new procedures demand near real-time data exchange between space agencies, with the Atlas incident already becoming a practical test of the system. Teams at the European Space Agency, for instance, have modified their Mars observation schedules, adjusting instrument timetables and sensor apertures to improve the odds of documenting potential fragment traces. At NASA's Jet Propulsion Laboratory, specialists have run new impact probability models, incorporating lessons learned from the Shoemaker-Levy 9 event but recalibrated for interstellar velocities and Martian gravitational conditions. The implications extend far beyond just one mission. A collision between a 3I/Atlas fragment and Mars, even something as diffuse as a dust plume, could inject a temporary haze of fine particles into the planet's thin atmosphere, potentially disrupting observational clarity for months. Engineers designing upcoming Mars landings are now accounting for the prospect of unpredictable debris zones. For experts in planetary defense, the situation serves as both a warning and an opportunity, a reminder that objects entering from other star systems present not only intellectual intrigue, but tangible risks to humanity's off-world ambitions. Coordination efforts have become truly international. NASA, ESA, and allied agencies are pushing to modernize their data networks, reducing the delay between detection and actionable response. Memorandums distributed in September advocate for broad access to raw astrometric and spectroscopic readings during high-interest events, marking a shift from the old model that prioritized peer review before release. The goal of this open data framework is to prevent any single research group or nation from retaining exclusive control over critical information that could impact the safety of billions of dollars in spacecraft, or, in the coming years, human explorers themselves. As scientists continue to debate the nature of Atlas's potential fragmentation, the larger significance is becoming increasingly apparent. Each interstellar arrival challenges not only our physical understanding of these wandering bodies, but also the infrastructure built to safeguard interplanetary missions. On July 1st, 2025, astronomers recorded the emergence of a second object trailing 3I/Atlas near Mars, the first suspected interstellar breakup ever observed at such a distance from the Sun. Unlike Shoemaker-Levy 9, which disintegrated before striking Jupiter in 1994, neither of the two prior interstellar visitors, 1I/Oumuamua and 2I/Borisov, showed definitive evidence of fragmenting. Current observations of Atlas include surprising spikes in carbon dioxide levels and measurable rotation changes logged by the Minor Planet Center and Gemini spectroscopic surveys. Though the trigger behind these anomalies remains under intense scrutiny, some researchers attribute the behavior to natural cometary separation, while others note irregularities that defy typical physical models. Despite continued study, There is still no unified conclusion about whether this fragmentation poses any threat to Mars operations or planetary defense efforts on Earth. What remains certain is that each new object from beyond our solar system brings fresh mysteries and motivates improvements in the global systems built to track them. As the scientific community awaits validation through peer-reviewed results, the unfolding story of 3I/Atlas is a powerful reminder that deep space holds vast unpredictability and that only continuous observation can reveal the truths traveling silently between the stars.
Initially, the discovery of 3I/Atlas seemed uneventful as it drifted quietly through our solar system. However, recent findings suggest that its trajectory has shifted and could now threaten Earth directly. The implications go far beyond local devastation. This could be an extinction-level event. Humanity stands at a crossroads, wondering whether we're truly ready for an unprecedented catastrophe or if something else is orchestrating this course change. The latest data defy expectations. The cosmos has presented us with an anomaly that's overwhelming experts. 3I/Atlas, an interstellar body around 20 kilometers wide, challenges every statistical model and is forcing astronomers to re-examine fundamental theories about space. Probabilities computed for its appearance simply do not add up when compared to natural trends. The vastness between stars is practically vacant, save for sparse particles and dust. Across decades of observation, stumbling upon an object like this should happen only once every 10,000 years, if ever. Instead, just after the surprising arrival of the first interstellar objects, we're suddenly faced with one that dwarfs all prior finds. The detection makes matters stranger. Contemporary telescopes use repeated imaging of identical sky segments, searching for movement between exposures. These instruments are tuned for trajectories typical of our solar system. In contrast, 3I/Atlas is moving at double the speed of anything human technology has launched, yet it falls neatly within detection limits. Normally, an object with such velocity would be untraceable, appearing as a mere streak in a single frame. A crucial detail is the path 3I/Atlas traveled into view. It approached via a background crowded with stars, its presence masked until July 1st, 2025, only becoming distinguishable when it reached the ideal spot for identification. The timing appears almost intentional, as if keeping hidden until a precise moment. The sequence of prior discoveries makes little logical sense. The first, Oumuamua, was diminutive and elongated. Its successor, 2I, resembled a typical comet. Now, 3I/Atlas is astonishingly large, jumping millions of sizes with nothing in between. This progression is too precise, raising suspicions about randomness. The object's trajectory intensifies the mystery. Instead of meandering, its path seems deliberately mapped, intersecting all significant bodies in our solar system. Its course is positioned within 5 degrees of the ecliptic plane, the shared orbit of all planets. Interstellar objects normally come from every conceivable direction, making such alignment incredibly improbable, 1 in 500 odds. More intriguingly, 3I/Atlas will graze Mars, Venus, and Jupiter, as it may on Venus, and Jupiter, as it may was old babies. Wilbus's ingestion, and Zendidas at Jupiter, as it may under May's mice. The sphere of the hypothesis, with the lilas, revisited. Calculations for a random body passing so closely to 3 separate planets yield a probability of just 1 in 20,000. The odds, while not impossible, are peculiar enough to make scientists wonder if unseen influences are at play. Adding complexity, its orbit is retrograde. It travels against the flow of planetary motion. On its own, this isn't remarkable. But for a mission aiming at prolonged planetary observation with minimal fuel, such an orbit would be ideal. It maximizes time spent near each planet, allowing extended analysis as the object approaches, passes, and recedes. A critical convergence is set for October 29, 2025, when 3I/Atlas will be at its closest to the Sun. At that exact moment, Earth will sit diametrically opposite beyond the Sun, shielded during the period of greatest radiation and heat. The chances of an interstellar object coincidentally steering clear of Earth at its most exposed moment are astronomical, hinting at intention over happenstance. NASA has categorized 3I Atlas as a comet and downplayed any dangers. Yet this classification doesn't fit. Typical comets, composed of icy dust, heat up near the sun, releasing gas in a predictable display, a phenomenon called sublimation that generates a trailing tail. Scientists rely on these behaviors to forecast brightness as a comet draws closer to solar heat. 3 Atlas, however, is defying all these expectations. When analyzed by the Hubble Space Telescope, instead of exhibiting the anticipated tail, the object revealed a curial shells, releasing data to predict. Oddly, this glow precedes the object, pointing towards the sun, not away as expected for natural comets. This is the opposite of established comet physics, where sunlight forces dust and gas into a trailing tail. The forward-directed emission suggests either an unknown natural process or perhaps artificial thrust. Even its light signature is perplexing. Its brightness and the manner in which it reflects sunlight contradict what's expected based on composition and shape. Some features raise the question of an artificially illuminated surface. Neither explanation fits the standard comet model. As it nears the sun over the next few months, the real test awaits if 3I Atlas fails to erupt with the conventional secondary tail and continues displaying anomalous brightness patterns. It would confirm that this is something never before observed. Its sheer scale produces another riddle, what researchers are now calling a scaling anomaly. Interstellar space is nearly empty, home to about 1 atom per cubic centimeter, a near-perfect vacuum. Rocky bodies, especially massive ones, should be immensely rare. The only natural phenomena powerful enough to launch a 20-kilometer object at enormous speeds are cosmic disasters, supernovas, planet-smashing collisions. Such events happen infrequently and scatter fragments in anticipated ways. Given these stats, encountering a body as large as 3I Atlas should be a once-in-many-millennia event. Yet, within only a few years, we've met a third interstellar newcomer, one so vast it strains the limits of known physics. The energy needed to propel something this big to these speeds is staggering, demanding powerful slingshot effects from stars or black holes. These events would typically shatter rocky bodies, not send them through space intact. And yet, 3I Atlas remains a cohesive formation, defying all prior expectations. 3 Atlas doesn't exhibit the chaotic spinning or erratic rotation normally expected from an object forcefully expelled from another star system. There's no visible fragmentation or major surface degradation, which should be inevitable after millions of years drifting through the brutal environment of interstellar space. Its thermal background presents another enigma. Spending possibly eons in regions close to absolute zero ought to leave characteristic imprints in its crystalline structures and outer material. When astronomers collect detailed spectroscopic readings from 3 Atlas, they'll be able to conclude whether its chemistry aligns with that of an ancient interstellar remnant or reveals strange inconsistencies pointing toward an entirely different origin. A separate mystery lies in the question of technology. Harvard astrophysicist Avi Loeb established what's now known as the Loeb scale, a 10-point index designed to assess the likelihood that an object represents extraterrestrial engineering rather than a natural phenomenon. A score of 0 corresponds to unmistakably natural origins, like an asteroid or ordinary comet, while a 10 represents definite artificial design, objects that change course, emit signals, or display other indicators of construction by intelligent beings. At present, Loeb places 3I Atlas at level 4 on this scale, meaning there's noteworthy evidence hinting at a technological basis, but not enough to be conclusive. That ranking arises from the numerous peculiarities associated with it, each of which could plausibly have natural causes, yet together resemble intentional design. Its mathematically precise trajectory, extraordinary size relative to earlier finds, and unusual behavior compared with typical cometary activity all push it further toward the artificial end of the spectrum. Modern observation systems now give scientists unprecedented ways to test these hypotheses. Radio arrays can detect any electromagnetic broadcasts suggesting active communication or power systems. Infrared instruments can register heat patterns indicating internal energy sources beyond simple solar warming. Even gravitational wave sensors might spot faint distortions in spacetime caused by exotic propulsion methods. The decisive phase will come as 3I Atlas nears the Sun in the next few months. Natural bodies of ice and rock predictably react to solar radiation. They warm up, vent gases, form tails, and undergo measurable changes in brightness and spectral qualities. Should 3I Atlas fail to display these behaviors, its rating on the technological probability scale would increase dramatically. Highly advanced alien machinery could rely on principles well outside human comprehension, such as controlled fusion, exotic matter physics, or electromagnetic field propulsion, each capable of creating the strange luminous emissions observed around the object. These mechanisms would produce distinctive patterns across the electromagnetic spectrum and even measurable gravitational ripples. Then there's the object's curious tendency to steer clear of Earth exactly during its closest solar approach. That scenario could represent extraordinary luck, or it could reflect deliberate navigation meant to minimize interaction with a potentially unpredictable technological species, while maximizing opportunities to study multiple planets. Finally, the academic response to these unconventional theories exposes deeper flaws within scientific culture. Research institutions have evolved into ecosystems that often reward caution over innovation. Many scientists now worry more about professional reputation than about following where the data leads. Funding systems reinforce this hesitancy. Those judging new proposals are usually the same colleagues most skeptical of radical ideas. It's like asking a critic who despises spicy food to sponsor a chili laboratory. This dynamic inevitably nudges researchers towards safe, incremental studies that pose no threat to established thinking, discouraging the kind of daring inquiry discoveries like 3I Atlas may require. Universities have gradually grown more politicized, introducing new obstacles to genuine scientific exploration. When academic institutions align too strongly with particular ideologies, they risk developing blind spots that distort how researchers approach contentious subjects. Science works best when it remains grounded in data and empirical facts, free from political influences that have nothing to do with uncovering the mechanics of the universe. The peer review process, once intended to uphold rigorous standards, has slowly turned into a gatekeeping mechanism. Reviewers now often judge studies based on adherence to established theories rather than their potential to foster real breakthroughs. This pattern creates a self-reinforcing cycle where only conservative, risk-free projects receive support, while ideas that might transform whole fields are dismissed long before they can be explored. History is full of examples showing how damaging that mindset can be. Quantum mechanics completely redefined modern physics, but initially met massive resistance because the concepts defied conventional logic. Even Albert Einstein struggled to embrace every part of quantum theory, illustrating how even the brightest minds can become trapped by their assumptions about reality. Today's academic reward structure compounds the problem. Universities and research bodies place heavier importance on how many papers a scientist publishes and how often those papers are cited, instead of rewarding genuine innovation. Scholars build careers through quantity, generating repetitive studies that reference each other's work, reinforcing intellectual echo chambers where the same viewpoints circulate endlessly. This system punishes unconventional thinking and suppresses the daring ideas necessary for true discovery and scientific revolution. A look at cosmic reality reveals an even more humbling picture. Mathematically, the odds of intelligent life existing elsewhere in the universe make the notion of human uniqueness seem absurd. Our own galaxy alone harbors around 1 billion stars, and countless of them likely sustain planetary systems capable of nurturing life. To claim that none of these billions of worlds ever birthed intelligent civilizations is like insisting that a street of identical houses stands completely empty while yours alone contains residents. The chronological argument strengthens this reality check. The Sun, at 4.6 billion years old, is a recent arrival when compared to the universe's 13.8 billion year age. Thus, other star systems had billions of years to form, evolve, and potentially develop advanced civilizations long before our own planet emerged. The earliest stars forged only hydrogen and helium and lacked the heavy elements required to build rocky planets and complex life. Over successive generations, the death and rebirth of these stars filled the cosmos with carbon, oxygen, silicon, and other life-essential elements. This enrichment made the creation of Earth-like planets possible billions of years before our solar system was even born. In cosmic terms, that means entire civilizations could have arisen, advanced, and traversed the Milky Way long before humanity existed. To grasp those timescales, consider that one of our current spacecraft, Voyager, would take under 1 billion years to cross our galaxy. Any society with just 1 billion-year technological advantage could already have explored every star system, including ours, without needing faster-than-light travel, only steady progress sustained over unimaginable timeframes. This broader cosmic understanding reshapes the central question entirely. The issue is no longer whether extraterrestrial intelligence exists, but whether human beings are perceptive enough to recognize it if it reveals itself close to home. Assuming an advanced species would communicate according to our expectations is a deeply anthropocentric notion that could blind us to more subtle modes of contact. Now, humanity faces what could be its most significant countdown. A critical deadline looms at the end of September 2025, by which time scientists expect a decisive answer about the true nature of 3I Atlas. The observational window is fleeting. Once October begins, the object will vanish behind the sun's glare, halting detailed examination for months. Avi Loeb anticipates the data will provide mathematical clarity. If the object consists of ice and rock, solar radiation should soon spark massive outgassing events and produce the bright tail characteristic of classical comets. However, if those expected eruptions fail to appear and the object continues to emit its unusual forward-directed glow, the implications will be nothing short of monumental. A 20-kilometer artificial construct entering our solar system would signify technology so advanced it would seem indistinguishable from magic. This critical period also underscores the formidable challenges faced by skywatchers. Ground observatories must contend with atmospheric distortion, cloud cover, and Earth's rotation, which limit observation times. Space-based tools like the Hubble telescope provide clearer views, but operate within restrictive scheduling systems planned months or years ahead for specific projects. In preparation, Loeb and his Galileo project have established dedicated monitoring facilities across the United States, calibrated to search for signs of artificial technology as 3I Atlas makes its solar pass. These observatories employ machine learning algorithms to screen every recorded object, isolating anomalies that deviate from natural behavior. Loeb has also instructed his team to remain alert through late October for peculiar atmospheric events around Earth that could imply the release of smaller probes or surveillance devices. If 3I Atlas ultimately proves to be artificial, it will mark the dawn of an entirely new era for humanity. One that could either unify us under a shared recognition of our place in a larger cosmic community, or deepen our internal divisions and prevent a coherent response to the greatest revelation in human history. The weeks ahead will determine which path our species takes and whether we possess the collective intelligence and maturity to comprehend that we might not be alone in the universe, but rather children finally awakening in a cosmos already inhabited by far older civilizations. And with that, what are your thoughts on the newest findings about 3I Atlas? Share them in the comments below, and don't forget to like and subscribe for more insightful content. For more insightful content.